I just want to move along. So our next presenter is Dr. Srihari. As most of you know, Dr. Srihari is a professor at the University of Buffalo, and today's talk is going to be on Cedar Fox and iFox. And Dr. Srihari, if you'll come on up, we'll get started.
Okay, a little bit of background. This talk is not going to be a real detailed computer science type of talk. Okay, I started as a computer scientist more than 40 years ago. I entered the field of artificial intelligence, and there was a hubris at that time that, everything human beings do can all be automated. That computers are going to replace human beings. This was 40 years ago, and I've been working in that field, AI. And then the way I got into forensics was we got a major project from the U.S. Postal Service to develop a system for reading handwritten postal addresses. And at that time, people felt that, I can't read my own handwriting. How can I get a computer to read handwriting, So anyway, we worked on that system, and many people contributed to those projects all over, but we did the first system for that. And today, about 96 or 97% of all handwritten mail in the postal stream is read by machines. We allowed the Postal Service to continue to be in existence for a few more years than it looks like it's going to be in terms of the economics. So that's what we did. And I came into this field because I was approached when the Daubert ruling came out, saying, you seem to know something about computer processing of handwriting. Maybe you can help this community by seeing how you can develop some automated systems for question document examination. And said, oh, what a nice challenge. So let me see if I can bring some of those techniques into this domain and see what we can do. And I was sure that we're going to do it all completely automatically. And so that's how we developed our early work, published in 2002 in the Journal of Forensic Sciences. We put together a system. We had all the tools in place. We had developed all these feature extraction algorithms for postal automation. We said, let's just plug all those feature extractors into it. They were all very abstract feature extractors, all kinds of features that no human being could understand what those features were. We plugged them all in, and then we had all these. We created this database that was referred to earlier on today, and we did, 96, 97% accuracy on those full pages of handwriting and so on. So it looked pretty good. Well, since then, I've had to take a hard look. Sachs criticized what I had to say, and a lot of his criticisms were good, actually. Saying, okay, you had a full page of text, you got diverse populations and all this type of stuff. So maybe I should be looking at, smaller amounts of writing and more similar writing and so on. And I concluded, we really should, we need to have better methods to be able to handle smaller amounts of writing. And also, we collected statistics of handwriting from a certain database. Will that really work with different populations? Those have to be learned too, and so on. So taking a hard look at all of this, I've now concluded after some 30-plus years in this field to see what is really the role of automation in the examination of handwritten items, lessons learned, and what could be done in the future. So my discussion today, I will begin by talking about what has been referred to as computational thinking. Computer science definitely has a role to play in almost everything human beings do, one of which is think computationally about whatever be the task at hand. And what is computational thinking? I'll talk about that briefly. And how computational thinking can come into question document examination, which can be thought of as reverse engineering, saying, okay, this is how human beings do this. How could we reverse engineering into this computer? And then I'll talk a little bit about the kinds of tools that could be used. The main bottom line is that I'm concluding that really we can't be saying that we can automate everything today of what question document examiners do, or in all of the forensic disciplines. I've had a chance to look at some of the other ones like footwear and latent prints and so on. All of these disciplines have the same kind of issues, and I've concluded that no, we're not ready for fully automating everything. We really should have tools that are going to be working with human beings. We can help them do their jobs better, but we're not going to be replacing them. And so what are those tools, and how does all this fit? And the big picture is, what is the computational thinking? So I'm going to kind of go through a little bit of this in the time that I have. All right, so the big issue, computational thinking. This was made famous by an early artificial intelligence researcher called Seymour Papert, who worked with Marvin Minsky at MIT, and then more recently by Jeanette Wing, she was at Carnegie Mellon. about this concept, computational thinking. It is a way to solve problems, design systems, and understand human behavior, drawing on concepts of computer science. We talk about some fundamental concepts we teach in a computer science 101 as to what does it take to write a computer program. So this is the kind of thinking that we do in computer science can be applied to a broader context of things that we do, like cooking a dish, right? What is the sequence of steps we go through in cooking a dish? Or what is the sequence of steps we go through in examining a handwritten item? So these are all things, can we kind of apply computational thinking to it? And my picture on the right, which you probably can't see at all, maybe you can see it on the printout, it's about how to cook. This whole thing is a chicken dinner for guests. And there are 3 parts to it: clean the house, cook, set the table, all right, and eat, drink, and be merry. Those are the 4 big circles. And clean the house has 2 parts: vacuum dining room and tidy up living room. Those are the 2 parts to it. And cooking involves 3 parts: do vegetables, shop for ingredients, roast chicken, and choose recipe. Okay, those are the. And then there are sub parts to it. Shop for ingredients has make shopping list and drive to the store. And then set table is find tablecloth, put out silverware, put out glassware, get plates out, napkins. All right, that's part of it. And then we got the final part. So this is kind of abstraction, saying there are major parts to it, and there are sub-parts to it, and so on. Of course, that's how we think about things. So this is simply saying that there is some kind of abstraction going on. One really doesn't need to mix up setting finding the tablecloth with vacuuming the dining room, things like that. There's not necessarily some interaction that goes on there. So that's called data hiding and so on. So this is the kind of thing that could be applied to anything human beings do, including forensics. So what are the major concepts of computational thinking? One is abstraction, which we just talked about. Abstraction is to understand and solve problems more effectively. Think about what are the major problems, sub-problems, things like that. The second part is of computational thinking is algorithmic thinking and mathematics. So to develop efficient, fair, and secure solutions. Algorithmic thinking is simply to be able to express your thoughts, saying these are the sequence of steps, I'm going to get into this loop, keep doing it until a certain condition is satisfied, or drop out of it when that happens. And of course, in making some of these things, we may want to bring in some mathematics in terms of what are the variables and how do they add up and things like that. And another aspect of computational thinking is understanding scale. That is, how does this scale up? What is efficiency? There are economic and social reasons for understanding scale. Cooking for 4 people invited to your house for dinner, will that scale up to having 100 people over for dinner? So that's a scaling thing, and does it computationally scale up? Maybe the combinatorial possibilities become so hard. In computer science, it becomes very hard very quickly, as I'll show in the case of handwriting. Even with a few variables, you're going to face enormous computational issues here, so scaling becomes an issue. Okay, so that's about computational thinking. Now again, this issue of relationship of computational thinking and law. This has also been looked at. A long dream of all of law has been logical rules to automate verdict. This has started from 1804, Napoleonic Code it's called. There's a manuscript shown at the right side here. To minimize discretion, maximize predictability of outcome. These are the kinds of goals for the Napoleonic Code in law. But it floundered because of vagueness of words and variations of the real world. All right? So people have made attempts in the early days of artificial intelligence, expert systems to replacements of the judiciary. Why do we need all this judiciary? Let's just have expert systems to do all of this. Well, they've had a poor record of both success and uptake. All right. On the other hand, better inroads have been made by legal reasoning systems which merely assist in making legal decisions. Example, construct hypotheses for evidence in a crime scene. So these are the possibilities that are presented to you, and remind the detective of hypotheses that they might have missed. So this is the kind of thing that they have made better inroads to have such legal systems. So this has been referred to as mind expanding. That is, you look at more possibilities, that expands your mind, avoids the pitfalls of mind narrowing, saying, why do we need a human here? Let's just simply do it all by computer. So mind expanding is a better thing to do with computers rather than mind narrowing. All right. So let's now, I've talked about computational thinking, I've talked about computational thinking and law, and let's get into computational thinking and forensics. So computational thinking is useful in domains where human judgment is involved. Human judgment is involved in terms of, what are the attributes, what are the features here, right? And I've found over the years that the biggest drawback of these automated systems for handwriting is getting those features right. Okay, we developed a postal system that did pretty well doing those features, but when I look at the fine variations, those features are not good enough. They do a reasonable job on large pages and things like that, but when we are looking at fine handwriting, those features were not good enough. Our human eye discriminates these things much better. You know, our retina and the neuro system that we have evolved over these millions of years are very good in terms of picking out these fine variations. And we have also thought, well, maybe our initial features for a postal system were too rough, and then let's think like, what are the features you give if you ask a document examiner? We have made those attempts. They're not still good enough. So there is human judgment that's coming into play. So that human judgment is involved here. And then also for computational thinking, we need to do some knowledge engineering, in the sense we need to sit down and ask the document examiner, how do you do this? So it's a starting point for creating artificial intelligence. An expert system involves interviewing a doctor, saying, what do you do? What are the things you do? And then you try and automate this stuff. And sometimes it's hard to get that knowledge engineering done right. But fortunately, in forensics, a lot of these have been already stated. Okay, what are the sequence of steps that we do? All your ASTM documents have had many of the experts sit together and say, well, these are the things we do. And so that is a good starting point, particularly with impression evidence, handwriting, latent prints, footwear marks, and so on. Much of the knowledge engineering has been done. And in handwriting, of course, success has been demonstrated in recognition. So it seems like it's a nice meeting point for computational thinking and forensics. So let's talk about the knowledge engineering for forensic document examination. I've got a couple of pictures here. These are the ASTM standards that were spoken of this morning. Standard guide for examination of handwritten items, and standard terminology for expressing conclusions of forensic document examiners. I was very happy to hear that this is all going to be in the public domain very soon, the end of this month or something like that. This has all been hidden from computer scientists because they're all copyrighted documents. So now we have a lot of this knowledge engineering available. We can say, we can look at it. Much of the knowledge engineering is available in these documents. It says what are the sequence of steps. We can now say, how can we have a computer program kind of follow these kinds of steps? There are many textbooks on handwriting examination. For example, there is something called the CAT principle. Are the documents comparable? Is the amount of handwriting you have adequate? Is the handwriting time contemporaneous? Things like these. These are all things have been expressed clearly. What are the characteristics of handwriting? What are class characteristics? What are individualizing characteristics? And we use, document examiners say that we use 7 S's: size, slant, spacing, shading, system, speed, and strokes. Right? Some of these kinds of things have been expressed clearly. So the knowledge engineering has been done. A computer scientist doesn't have to go and sit down and interview document examiners, because these are clearly expressed on many documents that are available. And then one of these, the ASTM documents, I was just looking at it. Where is the algorithm here? So you look at the ASTM document. It says these are the kinds of steps to do. Determine whether it's a Q versus Q, K versus K, or a Q versus K. And for Q and K, you ask the question, are these good quality? Are they copies? Are they distorted or disguised? What is the type and range? What are the individualizing characteristics? These are the kinds of questions to ask. So we can now, computer scientists can go back and say, how can I help in these things? Are they comparable? Are these two documents comparable? If not, ask for new and repeat, and then differences and similarities for conclusion. Here's just a word cloud. I took the ASTM procedure and fed it to a word cloud program. Came out like this, saying these are the words that are most important. So in a sense, getting what are the important things that are here. And here is a pseudocode for actually taking that. I wrote it as a computer program now. This is what a document examiner does. And the same idea has been written in the form of what we call a pseudocode. I call this as an interactive forensic examination system, or IFOX, in the sense this is the overall procedure, and there are sub-steps that we can contribute. We have the tools involve like individualizing characteristics, comparability, comparison, and adequacy. And how do we get hold of individualizing characteristics? Here are some examples of the most commonly encountered TH. And so what we decided, what I feel at this point is a human examiner should provide those features, saying you say that these are the features I'm using. Then we can help by saying, well, the features are given in this table. There are six characteristics of TH that actually comes from a paper of Muehlberger. He said for each of those features, these are the possible values. We simply take it from a human being to tell us what those features are. Then we get into computational mode, and then we calculate, for example, the TH on the left side is a high probability. It is 3 in 100. Whereas the second one is 7 in 100 million. All right, so that is so we can assign numbers now to these things, just like the DNA people do. That when you have this feature, how rare is that? And so we could calculate these kinds of things by looking at samples of handwriting. And so the problem here is computational. Actually, if you have 6 variables, with each of them taking 4 or 5 values, the number of probabilities you need is about 4,800. This is the combinatorial problem I spoke about. If you have for the word A and D, the number of possible probabilities can be as high as a million different probabilities, let alone how much data you need, right? So, and also we cannot assume independence. Right? If you assume 2 variables are independent, you can get nonsensical results. This is a very simple table I constructed about 2 variables about human beings, height and weight. They are not independent variables. They are dependent variables. If you assume they are independent and you multiply probabilities, you will get a ridiculous statement that short and light is 6 times more probable than tall and light. Okay. All right. So if you're, being short and light is very much more likely than being tall and light. And the other one is if tall and light, twice the probability of short and. So that's the correct one. Actually, this is the correct statement. All right. Short and light is 6 times more probable. Tall and light is twice probability of short and light. It's wrong. So this is the independence assumption. Right? So this is the correct statement. This is a wrong statement. So you get totally counterintuitive things if you assume independence. Should not assume independence. All right. So how do we do this thing? If you do not assume independence, you are facing a big computational problem. So for that, we are implementing a machine learning technique called probabilistic graphical models that take into account correlation between variables. Even if you have 6 variables, the number of possible combinations becomes very large. But by using some techniques like this, we can. So we have to learn these things. For this, we are implementing what are called Bayesian networks and learning algorithms. Very interesting that such a small problem becomes a big computer science problem in a class of problems called NP-hard. So there are, the chair tells me I have no more time left. So there is a type determination is something that again, a probabilistic analysis can do that. Opinion scales, likelihood ratios, and so on can be computed, then mapped into opinion scales from likelihood ratios. So I won't say anything more about that. Adequacy is a very interesting issue. One of the important things for a document examiner is, do you have adequate amount of handwriting sample here? How do you handle that? Quantitatively, there is a way of doing it. These are called as confidence intervals. As you get more and more samples, your confidence intervals become tighter and tighter and tighter. So statistically, we can help the document examiner figure out, do you have adequate data here, right? Otherwise, there is no simple way of saying, is there adequacy? All right. So some of these things are all available as automation tools, interactive tools rather than automations. Again, the main message I'm saying is all of these have to be interactive rather than saying we're going to replace the document examiner. It doesn't look likely in the near future. All right. So incorporate computational thinking and make it mind expanding. Probability allows considering characteristics otherwise ignored. So all of the things I said in the beginning are really applicable to handwriting. All right. So the work in progress are characteristics. Look, what characteristics do document examiners use? So what we are doing is interviewing document examiners to create or let them create the set of features they will use. And then we bring that in, and then we help learn the probabilities for all of these depending on different data sets. What we have to do now is create different learning tools, because you might one day be working with population from the 1980s or 20 years ago. Today's handwriting may be quite different from the Palmer style that was learned. Today we are doing Zener Blauser, right, in the schools. And maybe not even that. So the statistics and all that might change. So all the stuff that was done with old data may be totally irrelevant in today's world. And we have to relearn all this stuff, and that can be done if you have proper machine learning automation tools that will take samples and create new data sets, create new probabilities. All right. So in summary, the message I have is that computational thinking plus forensics, I call it, Katrina and I, we call it as computational forensics, all right, to be solved using abstraction, Algorithms, mathematics. Mathematics is important to do all those probability type of calculations, and of course scalability of these solutions. Okay, I'm out of time, so I'll stop here.
Do we have any questions from the floor? No online questions, so it's all up to you guys. Not one question. I'll ask a question. Okay, so in the introduction, I said the talk was about Cedar Fox and iFox. What is iFox? I know Cedar Fox.
That is just a concept. iFox is interactive forensic examination. The main theme with iFox is it stands for interactive forensic examination. Cedar Fox was developed as a pure automation tool. All right, so it's out there. It will tell you a yes or no and gives you some numbers with it and so on. I'm now saying we need to have a newer system where the features are not automatically computed. Cedar Fox does automatic computation, whereas iFox is saying, please enter all the feature values that you have. I'm going to take it from there. And it will give you mostly statistical results out of it that you can use to saying, what is the probable, how rare is this thing? How this particular combination of TH. So that is the kind of results it will give you when you feed it. So it's an interactive system rather than an automated system.
And that's available online as an online tool?
Right now, I'm just doing research on this thing. I'm a machine learning researcher, so I'm publishing this stuff in the machine learning community, saying this is a nice data set to work with. How are you going to construct those probabilistic graphical models, which are pretty complicated things that take into account the correlation between variables? That's the main thing it does for you. So we're just there. Once we finish that, we want to make it into a machine learning tool. You feed the samples, it will learn all the statistics from it, and then you can use it. So this is down the road and not available at this point.
Let's thank our speaker.